Welcome. Welcome. Today we're going to learn a little bit about the Laplace transform. The year was 1744. Pierre-Simon Laplace had just come on the scene with his new mathematical discombobulation that basically was going to change the world. So what the Laplace transform does, we're going to talk a little bit about the Laplace transform. We're going to look at the properties of the Laplace transform, and we're going to make a little table of Laplace transforms all of our own. And so with the Laplace transform, if we have a function, f of t, if we take the Laplace transform of that function, the Laplace transform, we get to use the uppercase s, and we're going to use the mechanical engineering Laplace transform, which is basically all you really have to do is change the lowercase letter into an uppercase letter, and instead of f of t, we're going to make it f of s. Now, of course, there is a definition for whatever the Laplace transform is. The Laplace transform is the integral from 0 to infinity, e to the minus st times f of t dt. So all we have to do is some integration now, and we'll be good to go. And many of the books pretend as though you could actually do this integration. We've talked a little bit in class about the unit step, u of t, and what the u of t is, and we're going to draw a little picture of what u of t looks like first of all. Remember, we talked about that in the land before time, u of t is always 0. And then in the land of time, u of t is just 1. And so that's what the u of t is. So if we plug this in, let's see. So what we're trying to do is we could say that the Laplace transform of u of t is equal to the integral from 0 to infinity of e to the minus st. U of t is just 1 dt, so now all we have to do is this integral. So many of the books pretend like we could really do this integral if we really wanted to. Well, maybe we can do this one. This is going to be, so the integral is 1 over s. There's a minus sign that goes with that. And then this is e to the minus st, and we just have to evaluate this from 0 to infinity. Let's go ahead and do that. That's going to be, this is e to the minus s times infinity. That's e to the st. Minus e to the minus s times 0, all of that over minus s. And so what we're going to end up with is, let's see, so what is e to the power infinity is just, it's a minus sign. E to the minus infinity, that's 0. And e to the power 0 is just 1. So this is going to be minus 1 over minus s, or 1 over s. And so that's the first element in our Laplace transform table. Let's just write that down here. We'll come over here and we'll make a little Laplace transform table. We're going to say, here we're going to say f of t in this column, and then over here we're going to say f of s in this column. And so when we say u of t in this column, what f of s is just 1 over s. So we've already done our table of Laplace transforms. So we could try one more. A lot of times there's 2 or 3 of these things that you can do by hand if you know how to do them. And so let's try one more here. Let's do f of t is equal to e to the minus at. So that's going to be an important one. That's one that we're going to want to know. And so then what we can say is that f of s is equal to the integral from 0 to infinity of e to the minus at, sorry, e to the minus st, e to the minus at dt. And so we can just combine those exponents here. This is going to be e to the minus s plus a t dt. And if we integrate that, that's going to be 1 over minus s plus a. That's all in parentheses. times e to the minus s plus a t evaluated from 0 to infinity. And if we put in the limits there, what we're going to get is that this is going to be 0 minus 1 over minus s plus a, which is going to be 1 over s plus a. Okay, so now we have a second element in our Laplace transform. We're going to say e to the minus at, and the Laplace transform of that is nothing more than s plus a. So now we have at least two. Actually, these are the two that we can probably do. And there's one more that seems like it should be easy, but it's not easy. And if you want to know how hard it is, just go look at the Khan Academy for delta of t. So delta is the Dirac delta function. What the delta of t is means that it's an impulse that has width. So delta of t is an impulse that has width. The area of it is 1. Area is equal to 1. And what they do is we're just going to keep making that bigger, taller, and taller until eventually all it is just an infinite spike of 0 width, but the area is still 1. And if you go look at the Khan Academy delta of t, it's harder to see, but delta of t is just equal to 1. So here we've got our table of Laplace transforms. We've kind of worked out a couple of example Laplace transforms, and now we're going to look a little bit at some of the properties of Laplace transforms, and then we'll find out how to use the Laplace transforms. Okay, we're ready to get started again here. What we've got is, we've got our table of Laplace transforms, hard-earned through mathematics, I might add. We've got our table of Laplace transform, and now I'm going to have to bore you only a little bit with, I'm going to have to bore you just a little bit with some of the properties of Laplace transform. So let's look at some of the properties. So some of the properties of Laplace transform. So let's see what we've got here. We can look at the multiplication by a constant. So we can say the Laplace transform of a times f of t, the Laplace transform, is equal to a times the Laplace transform of f of t. Oh, okay. So we can take the a out. If it's a constant, we can take it a out of the Laplace transform. We can also look at the Laplace transform of f of t plus g of t is equal to the Laplace transform of f of t plus the Laplace transform of g of t. So the nice thing about Laplace transforms is that you get a lot of chance. I should have put this down. This is equal to f of a times f of s. You get a lot of chance of using the cursive Laplace, the cursive L, and you get a lot of chance to use these curly brackets. And what we can do is we're going to say that this is equal to f of s plus g of s. So we can. This is the principle of superposition. One more that we're going to do that's a little harder. This is the Laplace transform of d by dt of f of t. So if we're going to take the derivative of using a Laplace transform, this is the one that gets a little tricky. This is s times f of s minus f of 0. So that's a derivative. Sometimes we can work it out hard enough. If we work hard enough on it, we can do the Laplace transform of d squared dt squared, d squared dt squared of f of t. So this is the second derivative. And so what we'd want to do is that, in this case, what we'd want to do is we'd want to say this is s times the Laplace transform of d by dt of f of t, right? So we take s times the function, so since that's squared, this is just one of those. And then we're going to subtract off here, this is df dt at time t equals 0. So now we have to worry about what does this look like. So we already know what this looks like. This is just going to be s and then we'll put some square brackets on here. This is S times S. So we know what the Laplace transform of d by dt is, because we can just, this is f times f of s, s times f of s minus f of 0 minus df dt at time t equals 0. And so another way that we can just finish that up, this is just s squared f of s minus s f of 0 minus f prime f dot df dt f dot, let me just do that way, df dt at time 0. Okay? So now, I guess we can do one more. Let me just do one more here just to round out everything. If we're going to do the Laplace transform of the integral of f of t, if we're going to do the Laplace transform of the integral, that's just 1 over s times f of s. And so this is one that we want to do, because this is where we find out in MATLAB in the simulate diagram why we get to use 1 over s as the integrator. Okay, so here's our table of, here's our properties for our Laplace transform. We have our table of Laplace transform. We have our properties of Laplace transform. We'll just try and keep our properties in our head as we go along here. Okay, welcome back. Goodness gracious. You'll never know how much trouble that is. Okay, so what we're going to do next is we're going to try and learn a little bit about, we'll try and practice using Laplace transforms ever so slightly. And here I'm going to divide, I'm going to put a mechanical system down here. Here's a spring, and I'm going to hook a damper to that spring, and I'm going to hook both of these things to the wall. So this is K, and this is B. And now what I'm going to do is I'm going to define this to be my output variable x. That's going to be x. So I'm interested in what x is going to be the output variable. And in this case, I'm going to put x of I is the input variable. And so maybe the first thing that I need to do is I need to draw a free body diagram of this point. There is no mass involved here, so I don't have to worry about that. What I could do is I can put a spring force here. This is K, and this is so K. If I move the spring towards this thing, I'm going to get a bigger force. This is K. This is xi, and if I allow x to move, then it's going to be minus x. And then as I move x, what I'm going to find is that I've got another force that's going to be b times x dot. And so those are the only forces that I have on this system. And so I'm just going to sum the forces, and I'm going to write the equation of motion. It's going to be b x dot plus k x minus xi. So I already incorporated one minus sign. You see, so that there's a minus sign because the arrows are going a different way, and that's equal to 0. And so another way that I can write this is just to say b x dot plus kx equals kxi. So here's my differential equation, and I'm ready to take the Laplace transform of this differential equation. So I'm just gonna say that right here. Let's take the Laplace transform of this entire equation. And then what we can do is we can use the principle of superposition. So whatever happens on one side of the differential of an equal sign, that happens on the other side. The equal sign still stands. So the first step that I can just do is this is just bx dot plus kx, the Laplace transform, is equal to the Laplace transform of k times xi. Now I'm going to start using some of our, so what first thing I'm going to do is I'm going to notice here that this is k times the Laplace transform of xi. Right, so I can take that out. And then the second thing I know that from Laplace transforms, I can break these two things into two pieces, so I'm going to do the Laplace transform. In fact, I'm just going to take the b out of there. Laplace b times the Laplace transform of x dot plus k times the Laplace transform of x. And so now I've done all the Laplace transforming that I need to do. I haven't changed anything here, and what I'm going to do is I'm going to still plug in what the Laplace transform is here. So I'm going to start up here again. So this is going to be b, and so I'm going to take the Laplace transform of x dot. So we'll start a square bracket here. The Laplace transform of x dot So let's see, that's just s times x of s minus x at time 0. That's the Laplace transform here. And then I can say plus k times x of s. So I just do the mechanical engineering Laplace transform. If it's a little x here, it's going to be a big X here. Sometimes I put the s as a function of s. Sometimes I might forget that. But I try and keep the capital letter thing so that you know that we're working in the s domain. And then this is just going to be easily enough. This is just k times xi. So here's my Laplace transform of my equation. And one of the things is I can break this into a couple different, I can break this into pieces. I can algebraically arrange this in a way that is maybe better for me. Let's see, so I'm going to do it this way. I'm going to say x of s times, this is going to be bs plus k is equal to k xi, and then this is going to be plus b x of 0. And one of the things is now, you know, what I can do, if like the reason we're solving this differential equation is we want to find out what x of t is. And even though this isn't x of t, it's closer to x of t than we are so far. So maybe we should just solve for that. So we'll say here, x of s is equal to k xi over bs plus k plus b x0 over bs plus k. And so one of the things that I want to point out to you here is that we've broken this thing up in such a way, what we're seeing is that the Laplace transform, once I've taken, this is the Laplace transform of the solution. If I know how to do the inverse Laplace transform, I'm going to be in good shape because I can just invert these Laplace transforms and I'll be good. And one of the things that I'm going to notice is that this one, this is the response due to the input x of I. This one is the response due to the initial condition x of 0. Right? So we've broken it. So we could do both of them. Like we may have a problem where we have an input and no initial condition, then we can throw this part away. We might do one where we have no initial condition but some kind of input, then we can throw this one away. Or we may have both of them. Right? So I just want to point out that we can do that. So let's just do, as an example, let's just say x of I is equal to 0, and let's just do just this part of it here and see how that works out for us. And so one of the things is that I can just do, I can say x of s due to the initial conditions only, I'll put a little IC here, is equal to x0 over s plus k over b. Now, you know, if I could get this into this, so one thing is that like our principle of superposition, our multiplication by a constant tells me that whatever x0 is, that's fine. And what I can do is I can multiply this s plus a. If I call that s plus a, and where I say, hey, a is equal to k over b, then, like I already have the inverse Laplace transform of this in my table. And so just by inspection, I can say xic of t is equal to e to the minus at, where I left one thing out, and I'd like to put that in here. Oh, this is going to be bad. It's hard to erase stuff sometimes. This should be x0, so that's x0 e to the minus at, right? I left out the constant. And we already know everything about a first-order system. This is just a first-order response, and we already know everything about a first-order response that we ever need to know if this is time. We know that this starts at x0. We know that at 1 times the time constant, 2 times the time constant, 3 times the time constant, and 4 times the time constant. We've already done this. At 1 times the time constant, this thing goes down. I don't want to do that either. We'll get rid of that. We'll want to do this as about 63%. So we know that at 1 times the time constant, it goes 63% of the way. We did those numbers too, but we also know that by the time we get to 4 times the time constant, it's essentially at 0. So we can just draw that one. And now all we have to do is we just get, maybe we get just a different color and we do a broad brush thing here. Woo! There we go. There we go. So that's what the response of that is going to look like. And so now we've done our first Laplace transform. We have a mechanical system. It may or may not have some initial conditions. We've done our Laplace transform. We've gotten to a point where we have a response due to the forcing function. We have a response due to the initial condition. And now we've solved for the response due to the initial condition. Wow. Okay, so now we're ready to solve for the response to the forcing function. Okay, we're back again. Hi. One of the things that we've done so far, we've solved we've solved the initial condition part of this problem. And now what we want to know is we want to find out what we know that x of s, just do the input. I'll just do a subscript of input, not to get it confused with IC, but this is the input. X of s of the input is, it's just going to be k times x I of s divided by bs plus k. So there's a lot of different algebraic manipulations that we might want to do with this. One of the things that we might want to do with it is say this is a k over b divided by s plus k over b times xi of s. And so we don't really know what xi of s is just now, but let's take an easy xi of s. So one of the reasons that I wanted you to go look at the Khan Academy, I wanted you to find out what delta of t is. So let's use the delta of t. So suppose x of I, this isn't good at all. I'm just going to leave this x sub ff. This is x of the forcing function is equal to xi. So I've got to get my nomenclature right here. So one of the things is that I can do is that then I can say that if for x of I can even do it differently than that. Let me do it just a little bit differently than that. Let's do x of I of t is equal to delta of t. And then my Laplace transform tells me that x I of s is equal to 1. So that's easy enough, because now all I have to do is just put this in here, and look what I've got. Well, we already did this one, right? I can just, if it's okay, I can just say x of the forcing function of t is equal to the inverse Laplace transform of k over b times 1 over s plus a. Oh, we already did that one. The only difference here is that there's a little bit difference because we've got a constant that's multiplied by it. So we don't have to do that one again, right? Because we already did that. So this is a first order response. In this case, the first order response, well, I mean, we can just do it. This is just going to be k over b e to the minus at, right? So we can just look at it, s plus a, k over b. So this is just a little bit different magnitude first order response. And now what we're going to look at is what happens when x of I is not the Dirac delta function. Let's let x of I be u of t. X of the forcing function of t is equal to u of t. So this is where it gets bad. I'm gonna multiply this times some number n. So it can be whatever number it is. And I'll try to keep carrying this n through, but if I forget it somewhere along the line, you'll know that wherever this u of t is, I can scale the u of t bigger or smaller by multiplying it by some number n. Right? Okay, so what we can see is that in this case, x of s is equal to, so this is k over b divided by s plus k over b. And now we have to multiply this times 1 over s. And I'm going to make this s a little bit different. So I'm going to say this is also s times 0. That's 1 over s plus 0. I'm emphasizing this because this has a root that is minus k over b. This says s equals minus k over b. And this one says that s is equal to 0. So these both of these parts have those roots. And what would be really nice if in some way, if there was only some way, if only there was some way that I could break this up in so that I had two pieces of it that look like this, s plus k over b plus b over s plus 0. Because if I could do that, I can just look at my table of Laplace transform and say, hey, I know what the answer to this one is. This one's easy. It would just be, here, I'm going to do it in this direction in a different color. This one would be easy. It would just be a e to the minus k over b times t. And this one would be easy too, because it would just be b over s, right? Because I just do the inverse Laplace transform of that. And so now if I can break it into these two parts, I'm in good shape. And so now the trick is I have to figure out, like, how do I break that into two different parts? And so one of the things that I see here, oh, shoot, I think I'm going to have to, sorry, I'm going to have to erase this one a little bit. So I put it in the wrong place. Let's put this as b over s. Oh, sorry, that's not b over s at all. It's just b times u of t. Sorry, I was a little bit wrong, right? So that's so what I'm going to do here is I'm going to take this part of the equation and I'm going to say, you know, I think I would like to multiply this whole thing. If I multiply this whole thing by s plus k over b. If I multiply the whole thing by s plus k over b, then what I get on this side is this is just a plus s plus k over b times b divided by s plus 0. And then what's on this side? So what's on this side is my original x of s. So I'm just going to put that x of s. This is the original total function on this side. It's the whole total function, but I multiplied it by s plus k over b. Right? So I've got the whole function over here. So now I've got a. And I could try and solve for a, but this thing's going to get in the way. But you know, there's one place here that if I was tricky about it, one of the things that I could do is if I evaluate this whole thing at s equals minus k over b. So I'm going to evaluate this whole thing at this root. Guess what happens? What happens when I put minus k over b plus k over b equals 0? Ta-da! I've made that disappear. And so now, here's a formula that we've just derived that we can use. We can say a is, so whatever coefficient we're looking for is equal to the root that we're interested in, s plus k over b, times the entire function x of s, times the entire function. And then all we have to do is we have to evaluate it at s equals the root that we're interested in. So let's try doing that. So in this case, what we've got is so one of the things that happens, is that we've got an s plus k over b. So we've got the root of interest, and we've got the entire function, that's k over b, and we're going to divide that by s plus k over b, and then we're going to divide that by s plus 0. Sometimes we don't need to use the 0, but we have to evaluate this whole thing at s equals minus k over b. So this would be a problem. If I just plug in minus k over b for this thing, that could be a problem because this would go to 0. Then I have a 0 on the denominator. We don't know what happens when the stuff gets on the denominator. But the good news is that stuff cancels out. And all I really have to do is this is just when s is equal to minus k over b, this is k over b, and this is minus k over b. So this is minus 1. So a is equal to minus 1. Ha! Can we do b as easily? Let me see if I have a little bit of space left over somewhere that I can do b really quickly. B is equal to, so it's the root of interest, s, times the entire function, which is k over b divided by s plus k over b times s, evaluated at s equals 0. So the good news, again, the good news is those s's cancel out. We're just going to make k over s equals 0, so that's just 1. K over b over k over b. So now we know what a and we know what b are, and we can do the inverse Laplace transform. Sorry, I'm kind of running out of space here, so what I'm going to do is I'm just going to do it up here. Let me see if I can find a different color that may or may not be brighter. I don't know. Colors aren't working very well sometimes here. And so what I'm going to do is I'm going to say then x of t due to the forcing function is just equal to 1e to the minus k over bt plus 1 plus b, which is just 1, times the unit input is just 1. U of t just equals 1, right? So that's just 1. But I've made a bad thing here. The a happens to have a minus sign on it. And so if I really want to do this, now I have to get rid of this. X of t is equal to 1 minus e to the minus k over b times t. And that looks like a unit step. Oh, we can do any part of them. Remember, we've got all the parts. We've got the parts. We already did the initial condition, and so now we've done this one too. So now we're all set. Hello again. All right, so we know a little bit about Laplace transforms now. We should probably try to work out a little bit more difficult problem. This isn't too difficult. This is one that we've already done in class. We did it a different way, so we already know what the right answer is. So let's just do that one again, and that is that 2x double dot plus 22x dot plus 20x equals 20f of t, right? So we're going to do that. And you can do it if you don't put this into canonical form, but putting it into canonical form makes some difference and it helps a little bit. So I'm going to do that right now. Plus 11x dot plus 20. Oh, shoot. It's not 20x. 10x equals 10f. Okay? So I just put it into canonical form. Well, we better take the Laplace transform of everything. We'll take the Laplace transform on both sides. And I'm just going to do the Laplace transform as fast as I can, even though I'm going to include initial conditions, even though in our problem here, I better write this down. X of 0 equals 0. X dot of 0 equals 0. Those were equal, and f of t is equal to the unit step function. So we already did that in here. We could do other numbers. It just makes the algebra different, and you could work these out yourself and give that a try. So here's what we're going to do. We're going to take the Laplace transform. So this is s squared x minus sx0 minus x dot 0. That's the x double dot. Plus 11sx minus 11x0. So that's x dot. And then plus 10x. This is a capital X here, if you can't tell what that is. is equal to 10 f of s. Right? So there we go. And so now all our job is since we're trying to find x, we might as well solve for x. We're going to say x of s. Sometimes I use the s, sometimes I'm just sloppy and I don't. X of s, oops, don't let me do too many things at one time. So this is going to be s squared plus 11s plus 10 is equal to 10 f of s minus plus 11 x0 plus x dot 0. Right? So the first thing, let me go ahead and do one more. So let's do one more. X is equal to, so this is 10f over s plus 1, s plus 10. So there's a couple things that we probably ought to note here. So here, this guy right here, this is the characteristic equation. You can go see lecture 5. Lecture 5 tells you that the roots are lambda 1 is equal to minus 1, lambda 2 is equal to minus 10. So we've already figured that out. If you can't use the quadratic formula, this is a good time to practice. And so we've got our x is equal to this, and then we can say this is 11x0 over s plus 1, s plus 10. You know I'm going to do this one differently. X dot 0 over s squared plus 11s plus 10. So either way I can do it. And what I want to emphasize is this is the response due to the initial velocity. This is the response due to the initial position. Both of those are 0 in our case. So I can just get to scratch those out. 0. 0. Both of those are 0 in this case. This one is the response to the forcing function. That's the response to the forcing function. We don't know very many forcing functions, but what I can say, if f of t is equal to u of t, then I can also say that f of s is equal to 1 over s. Right? I just go to my Laplace transform, boom, I'm done with that. And so now if I'd like to solve this, x is equal to, well, I know what it is. This is 10 over s plus 0. If I want to do it this way, I can do s plus 0 times, this is going to be 1 over s plus 1 times 1 over s plus 10. So this is the whole function that I'm interested in. Sometimes I don't even need to put that s plus 0 in there, but that's okay. I'll leave it in there. And you know what I'd really like to do is I'd like to break this into pieces, smaller pieces, and if I could just break it into small enough pieces, I could break it into a piece that would look like this, a0 over s, because that's s plus 0, plus a1 over s plus 1, if I could do that. And then I could do another one that would be plus a2 over s plus 10. Those, and if I could do that, right, if I can do it, if I can get it into this form, I can just use my table of Laplace transforms. It's easy peasy, easy as pie. And so I'm going to write out what the function, I'm going to write out what the general formula is, and then I'm going to use that general formula. So here's what the formula is. The formula is, I'm going to say that a sub I is equal to the root of interest. It's the root of interest times the whole function. But it's evaluated at s is equal to the root of interest. Right? So if you want to figure this out, here's what this is the formula. So now that we've got a formula, why don't we just try and use the formula here? So let's see. A0 is equal to the root of interest, that's s, times the whole function, which is 10 over s plus 1, s plus 10. Now, we're going to evaluate this at s equals 0. So one of the things about it is that this would get problematic. If we put s equals 0 in here, that's going to get problematic. So one of the things that always happens is that s can cancel out. I'm going to substitute in s equals 0 here. So this is going to be 10 over 10, 1. Perfect. That was easy enough. And now I'm going to look at whatever a1 is. So it's the root of interest. This is s plus 1. Times the whole function, which is 10 over s plus 1, s plus 10. Evaluate it at s equals minus 10. I'm probably going to have to, so those cancel out. We notice that that's going to cancel out, right? And now I'm going to have to plug in for s equals minus 10 here. Oh, well, it's not s equals minus 10. Sorry. It's the root of interest, and I'm evaluating at that root, which is s equals minus 1. So this is going to be minus 1, so this is going to be 10 over minus 1 times, this is minus 1 plus 10. So you can do all that math out. Let's see, so this is, that's 9, 10 over 9, but there's a minus sign on it, so that's minus 10 over 9. That's A1. And now I'm going to do A2. A2 is equal to the root of interest, s plus 10. S plus 10. It's the root of interest, s plus 10, times the whole function, 10 over s plus 1, s plus 10, evaluated at s equals minus 10. This time I have a little bit more room down here I can plug in. This is going to be, so the good news is let's cancel those things out. That cancels out because we don't want to divide by 0. And that's going to be 10 over minus 10 times minus 10 plus 1. So 10 over minus 10 is minus 1. And minus 10 plus 1 is 9, so that's going to be 1/9. Now, if you go look, those are the same ones that we got in Lecture 5. It's the same ones that we got in Lecture 5. But what's important about this is that now I can just plug this in, easy peasy. This is A0, right? If I do A0 over S, if I do the inverse Laplace transform, that's just A0 plus A1 e to the minus 1t plus A2 e to the minus 10t. 10t A2. Sorry, I ran it. This is x of t is equal to that. Boom. I'm all done. And I'll send out some sample problems with this too, and you can give them a try by yourself. Thank you.